So there's a lot of geometry words in the title, but actually I want to spend most of the talk talking about something very elementary. And it's a topic that I'm very fond of, so hopefully I convince you to also be fond of it. So it's something I call isomorphisms on sale. And the notion of on sale is the same one as like you go shopping and you want to buy this shirt and it's $100. But I mean, what shirt should cost $100? So you wait for it to go on sale and you buy it for $35, right? So I want to buy isomorphisms for a steep discount. So that's the punchline. And so let me explain what I mean. So first. In Representation Theory 101, what we learn is that at least when you're in the simplest possible context, you have complex representations of finite groups, then representations are completely determined by their characters. So you just take your representation, which is a map to GLN, you compose with the trace function from GLN to C, and that remembers at least the isomorphism class of representation. So we know that two representations, pi1 and pi2, are isomorphic if and only if their characters, which I'll denote by a big theta, is equal to pi2. Okay, and so this, in some sense, is already an isomorphism on sale. I mean, you don't actually get the isomorphism, but you get the fact that they are isomorphic at the cost of just comparing two scalar-valued functions. So in some sense, this is the most classical isomorphism on sale. And so now let me give a super baby example. I mean, like the opposite. Okay, well, I mean a baby example. So I just hesitate because, like a superhuman is usually better than human, but I mean something less. So, so example one is suppose I take my group G to be a cyclic group of order n, let's say, and I take pi1 and pi2. And I'll do this I'll probably forget to write this, so let me just declare now that if I have two representations, then I'm always going to declare them to be irreducible before I start my comparison on sale. Okay, so I have two irreducible representations of a cyclic group, and we know that the irreducible representations of abelian groups is very simple. They're just one-dimensional. And so both of these are just homomorphisms to C star. Right? And of course, if you have a cyclic group, then a homomorphism to C star is determined by where you send a generator. And so an example of an isomorphism on sale statement is that pi1 is isomorphic to pi2 if and only if, not only, I mean, of course this is true, but actually I only have to check at a generator. Okay, so this is a super baby example. So there's very little content here, but I just want to give you some flavor of what isomorphism on sale means. Okay, so that was baby example. Now let me give just baby example. Okay, so probably this is everyone's first favorite group of something very simple. Probably everyone's next favorite group of something non-abelian is the group of, let me put a P here, upper triangular unipotent matrices with coefficients in FP. This is called the Heisenberg group. It's a very famous group. So let me write down the statement. So pi1 and pi2 irreducible representations are isomorphic for this group if and only if the character at this element is equal to this element, provided that it does not have norm 1. Okay, so that's another example. And this is quite a non-trivial statement because, I mean, this is an interesting group. It has interesting representation theory. If you know anything about this group, it has very beautiful representation theory. The irreducible representations of this are either one-dimensional or they are p-dimensional. And if they are p-dimensional, they are completely characterized by the action of the center. And the center of this group is this top right-hand corner. And because I've set Fp here, the center is cyclic. And so I just have to check what the central character is doing, which is determined by what 1 is doing. So after you apply some theory, then this example is just only slightly harder than this example. But it already looks much more interesting, right? OK. And so the class of groups that I'll focus the rest of the talk on are groups like GL2FQ. And so let me give some examples about GL2FQ. Yeah. So OK. So right. So how I should say it is like this. This is isomorphic to this if and only if this thing is true and both of them are not. OK, I see what you're saying. I understand what you're saying. OK. Let's say the dimensions of P. OK. Oh yeah. So OK. Yes. So both of them are always irreducible. OK. Yes, I agree. Yes. Very good. Thank you. Yes. Perfect. OK. Is this the correct one? It doesn't look correct. OK. It looks like there should be. I don't know who made that statement, but does someone know how to turn on the ones here? No change. Well, I will continue, and if someone wants to figure it out, then they can figure it out. OK, so the next one I want to do is GL2FQ. OK, so a very particularly nice subgroup of GL2FQ is a set of diagonal matrices inside here. And this group is good for representation theory. Well, OK. Another thing that you can do is you can define the upper triangular ones, call it B. And so what this tells you is that, OK, well, this might be a very interesting group, but this is an abelian group. It has easy representation theory. Given any character over here, I can pull it back to a representation here, and I can induce. So this process, a lot of the time, gives you an irreducible representation, but not all the time. And so, OK, so let me define first the parabolic induction, GL2FQ, of theta to be the induction from B of FQ to GL2FQ of theta composed with this map here. We'll call it projection. OK. And also in Representation Theory 101, what you learn is how to calculate the character of such a thing. And it's quite easy. So I'm going to call this representation pi t theta. If I take the character of pi t theta at some element g inside my group, this is just an averaging process. of theta of projection of in. Okay, so it's a nice, clean formula, but doesn't look like it immediately gives you numbers. So let me specialize to a setting where the formula looks very easy to digest. So let's say, assume, okay, so take G with distinct eigenvalues. Okay, so in other words, take G to be regular semisimple. So now I take a 2 by 2 matrix with coefficients in FQ. Its characteristic polynomial is a degree 2 polynomial with coefficients in FQ. That means that the eigenvalues are either in FQ or they're in FQ squared. So those are the only two possibilities. And so I can write this down as my two possibilities. So either G has eigenvalues, let's say A and B inside FQ, or it has eigenvalues alpha and alpha bar inside FQ squared, not in FQ. So those are the only two possibilities. Okay, and so one can ask, for such a G, what does this specialize to? And that's that's an explicit computation that you can do. And here's the answer, is that this thing is going to be equal to, well, in this case, you can calculate that if A and B are different, then there's, once you've put it inside B of FQ, there's only one other way to put it inside FQ. Either you put it in as like AB, or you put it in as BA. Those are the only possibilities. And so what this formula gives you is that it's going to be theta of AB plus theta BA. Okay, so that's the case in the first, yeah. Now, in this second situation, when the eigenvalues are alpha and alpha bar, where alpha is something that's really not in FQ, then actually there's no way to conjugate it into something in B of FQ, right? Because something upper triangular, the eigenvalues are just the things along the diagonal, and so you can't do that. And so this is 0. So this it's a sum over nothing, so it's 0. So this is a very nice formula that just comes from specializing this to the regular semisimple part. And this formula, this kind of formula, is very important to me, so I'll give it a name. I'll call this star T theta. Okay. Okay. So I guess okay. So here's the theorem. Oh, it stops there. I see. Which I'll attribute to Green. But to be honest, I can't be certain that he would have cared about this. So first, when is such this representation irreducible? It's irreducible if there's some A and B for which theta of AB is not the same as theta of BA. Okay, so this is a genericity assumption, and we'll often use this. So I'll say theta in general position, which means exactly the thing that I just said. So this statement is to guarantee that this pi t theta is irreducible. Okay. Then the statement is the following thing. Okay. Some other irreducible representation, pi, is isomorphic to pi t theta if and only if its restriction, the restriction of the character to the regular semisimple part, is equal to this thing here on the regular semisimple part. So in other words, if you have some other random irreducible representation, in order to determine whether it came from parabolic induction, all you have to determine is what the character values are on the regular semisimple locus, and it'll either be this formula or it's not this formula, and that completely determines the behavior. Okay, so now there's some problem here, and the problem is that, like, say you were in F2, if you're in F2, then you don't have so many non-zero elements. So in particular, you can't choose two that are different. And so, so this, so you won't ever have anything lying in this first case. So it's not so good to work in this situation. So, but there are other things that can happen for small q as well. Not just q equals 2. I mean, q equals 2, maybe you don't even have any theta in general position. So that's also vacuous. But anyway, one must be a little bit careful about q. I will assume q to be sufficiently large. And then later, I'll actually give you a proof of this kind of statement. And so you get a sense of how big this q needs to be. OK, so now, if you haven't seen the representation theory of GL2FQ before, let me just tell you that the representation of theory of GL2FQ basically breaks into two parts. So there's the stuff that looks like what I've told you here, and there's the stuff that doesn't. And given the exposition, one natural thing to consider is, well, I have if this or this, right? I could maybe see if the opposite happens, and that's true. So let me phrase this in the following way. Maybe I write it a little bit more slowly for, OK. So consider some element that looks like this. OK, so inside GL2FQ, if you calculate, which I did this morning just to make extra sure, which involved me like looking at what is the quadratic formula again. But the eigenvalues of this are a plus or minus b square root d. Okay, and so that means that if I choose d so that square root of d is not in FQ, then this, and I choose, and so in particular d is not 0, then this thing will be something that has distinct eigenvalues, and it'll be something in this second case, right? And so let's do that. So choose d so that square root of d is not in FQ. And then what I can do is I can consider some group that I'll call T prime, which is just defined to be all things that look like this. A, B are allowed to vary, and then my D is fixed. OK. And this thing is, I mean, I've already told you what goes on here. This thing is isomorphic to FQ, adjoint square root of D star. And this is FQ squared star. So everything can be made very explicit. And so this is in this kind of alpha setting. And I can consider now characters of this abelian group. And so one can wonder whether there's some way to cook up a representation of GL2FQ from the data of this character over here. Something like this, but of course this can't work because of previous said reason that you can't put this stuff inside B. And so there's a fancy way of doing it, but Green had explicit ways of doing this. So let me write down Green's theorem. So it's still 1955. So I assume theta is in general position. And in this case, that means that there's some alpha for which theta of alpha is not the same as theta of alpha bar. And this is, again, to guarantee some kind of irreducibility. OK, so first, you can construct irreps, or an irrep, pi t prime theta associated to this data as well. So that's part of this kind of an existence thing. And moreover, one has an isomorphism on sale statement similar to over here. OK, but before I say that, I should say, and the character formula of this pi t prime theta is going to be equal to, at G regular semisimple, has the same shape except with the 0 and the non-zero part flipped. So it'll be 0 if the eigenvalues are inside FQ, and it will be theta of alpha plus theta of alpha bar if the eigenvalues are in the second case. OK, so it's a small lie. This is actually, there's a minus here. But And so I'll again call this kind of formula star sub t theta, except I remember which t that I'm working with, so in this case, t prime. Okay. And so the isomorphism on sale statement over here is that pi is isomorphic to pi t theta, t prime theta, sorry, if and only if this on the regular semisimple locus is equal to this, pi t prime theta on the regular semisimple locus. And again, part of the worth here is that the formula here is very easy. It's simply equal to this star t prime theta. Okay, so again, I need a largeness condition on Q. Okay. Yeah, there's an analog and characteristic too, yes. Oh, it's so shiny. Okay, so let me write down the general statement now. So I wrote down only for GL2 over here, but actually this is something that happens for all G of FQ for G a connected reductive group. Okay, and so, general case. So in the general setting, notice that this theorem is kind of, there's two parts. One part is to produce a representation satisfying this property, that it has character equal to star t theta on the regular semisimple locus. And then the other part is that to show that that's the only representation that has that property. So it's kind of existence and uniqueness, right? So for existence, this is due to Deligne and Lusztig. So we have existence. So maybe I don't write this down, but so what Deligne and Lusztig do in their very famous paper in 1976 is they construct from the data of a maximal torus inside a connected reductive group G, together with some chosen theta, they construct from this a representation of G of FQ. And this representation is often called RTG theta, and it's defined to be the following thing. You take the cohomology, well, you take all of them, you take alternating sum of the cohomology of, okay, let me finish writing it, and then I'll say, with theta here. Okay, so let's unpack this. So LQ here means the Lang map, and so this is by definition just all G's inside my connected reductive G, such that G inverse sigma of G, sigma is my Frobenius, lies inside U. And this thing naturally has two commuting actions. It has a action by G of FQ on the left, because if you act by like left multiplication by gamma, when you put it over here, the inverse puts it into the middle, but that's sigma fixed, so it cancels out in the middle. And it also has a right action by the t that you started with over there. So this t is related to the u in that t is normalizes this u. Note, however, that, okay, it's a bit subtle point, but this u may not be defined over FQ, but it's just something that lives out in FQ bar. Okay. Yes, correct. So what I do is I take an FQ rational t. That thing, if you base change over FQ bar, is a split torus now. You can choose a B that contains it, and you take U to be the unipotent radical of that thing. And that thing is still normalized by, all of T of FQ bar, but in particular T of FQ. And that normalization is important for just the sigma part in this action, because if I multiply on the right, then it will spit out on this side, and a sigma of it will split on this side. And if that thing was in my FQ points, then it's sigma stable, and that will then normalize this guy. Okay, and so this inside variety is this thing, which comes with these commuting actions. And so I can, given any character of theta, look at the subspace where the t acts in that prescribed way, and that leaves only the interesting g of fq action. And now I take alternating sum of this. So it's not really a representation, it's a virtual representation, but okay. Okay, and so this is, this thing here, this is our pi t theta in general. That's the general version of this. And so actually even to this day, outside of special cases, one actually doesn't know how to define pi t theta without using geometry. So in GLN you can do it, in SP you can do it, and maybe in some, like, so a couple other examples you can do it. But in general, this is the only known way to get at these representations. Okay, so let me state now the, okay, maybe a fact here is that, that if you calculate the character of this at G regular semi-simple, actually it's, in terms of the geometry, it's kind of very easy. There's a formula that allows you to rephrase this in terms of fixed points of some action on this U, and you can imagine, like, if you have a regular semi-simple element inside your torus that conjugates this, like, how many fixed points is it going to have? Like, nothing except identity. And so for that reason, the formula of this is very simple. It's either going to be a sum over the Weyl group, theta W, if G is conjugate to an element of T of FQ, or it's 0. And so this is the general form of the star T theta. Okay, so this is kind of the existence part. This is showing that there are representations that have this formula. And then the uniqueness part is then the following result. So let me state it first. Okay, actually, okay, yeah. Okay, so the statement is that if I have an irreducible representation pi of something like GL to G of FQ, then this is going to be isomorphic to pi t theta, which is this RTG theta right here, if and only if the restriction to the regular semi-simple locus agrees for the two things. Okay, so say again. Pi is virtual now. It's a virtual irreducible, so it's plus or minus irreducible. So that's why I was like a little bit not too concerned with the fact that I had a minus sign over here. Actually, in terms of geometry, the reason that this minus sign appears is that the Deligne-Lusztig variety for GL2FQ in the non-split setting, the interesting part of the cohomology is in H1. And so when you take this alternating sum, a -1 pops out. And so that's why, like, in this formula, I don't have a minus sign, but that's because, like, on this side, there was actually a minus sign. Yeah. Correct. Yeah, so I assume that theta is in general position. And I also assume that Q is sufficiently large. Okay. Yeah, but then the sign is determined because, yeah. Yes, that's correct. Correct, exactly, yes. No, it is in the dimension. It's in the middle. It's in the middle degree, which is, and the middle degree is equal to the dimension of the Deligne-Lusztig variety.
But do you know that the interesting cohomology is only in the middle degree?
So under this constraint, it will be only in the middle degree. That statement is true. Okay, so again, I'll put some attributions here. So say, and let me finish the list first. 1979. 1990. Okay, so green, as I've attributed up there, is more generally for this statement for GLN FQ. And Lusztig proved this for all G of FQ. You can find a short article by Lusztig in around 2020 or 2021, writing this the proof down. NER considered this in a p-adic setting, so F is a non-Archimedean local field here. And I mean, one has to be careful what kinds of T are allowed, but let me just write it like this. So this is the first case where this kind of question was considered for representations of p-adic groups. And then my collaborator Masao Oi and I considered this in a variety of contexts for some reasons that I will reveal later on in the talk. And these are the kinds of settings that so we have some version of this. I mean, we have a different proof of Lusztig's theorem in general position setting, and so that's the meaning of this. Then there's also a version that works for parahoric groups. So this means like instead of GLN FQ, you consider a GLN of ZP or something like that. And then we also have a version that works for p-adic groups. But what I'd like to do next is to give you our proof in the G of FQ setting. Okay. Okay. So let me. Okay. 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 Okay, so the proof is very elementary, and so I like to talk about it. And the proof also uses Cauchy-Schwarz, and so I'm happy. Okay, so what is our task? Our task is, our assumptions are that we have two irreducible representations, pi1 and pi2, irreducible. And we also know that their characters on the regular semi-simple part are the same. And moreover, we can use this, what the shape is, that it's equal to star t theta. Okay. Okay. So now I have two irreducible representations. I want to show that they're isomorphic. I can show that their inner product is 1. Right? But for two irreducible representations, either inner product is 1 or 0. There's only two choices. So it's enough to just show that it's not 0. Yeah? So it's enough to show that the inner product of pi1 and pi2 is not 0. So that's our goal. Of course, this inner product is defined by some averaging process, right? You average over the product of these values. So I can, of course, average over the regular semi-simple part, and then average over the not regular semi-simple part, and then add them at the end, right? And so I can split up this thing as pi1, pi2, regular semi-simple, and pi1, pi2, not regular semi-simple. I'll just say not, okay? Okay. So my only task here is to show that this thing cannot cancel with this thing. That's my goal. Okay. So now observe. If I consider this not part, then by Cauchy-Schwarz, this thing is less than or equal to the inner product of pi1 with itself on the not part, half, times pi2 and pi2 on the not part, 1/2. And these things are automatically positives, actually, so I don't have to put these things here. It's just like this. Okay? Okay, so that's the first. This is Cauchy-Schwarz. Okay, so now what do we know? We have these two representations, pi1 and pi2, pi2, pi2. And we know that they're both irreducible, so definitely these two things are equal. On the other hand, for each of them independently, I can split them up into the regular semisimple part and the not. And our assumption is that these two things are equal. So of course, these last two things are also equal. So these two parts are equal, and this is just equal to pi 1, not. Okay? Okay, so now imagine, suppose that this thing was less than 1/2. If this is less than 1/2, well, that means that this thing is less than 1/2. That's the same quantity. But these two things sum to 1, right? So that means that this thing is bigger than 1/2. So then what we would have is that we would have a situation where this thing, which is, by assumption, absolute value bigger than 1/2 now, and then this thing, which is now bounded above by Cauchy-Schwarz by this thing that's less than 1/2. And so this thing would be less than 1/2 in absolute value. This is bigger. Oh, no. Wait. Huh? Yes, that's, wait. Inequality is so difficult. Okay, so this thing is bigger than 1/2, this thing is less than 1/2, and there's just, if you have in absolute value, right, there's just no way for these two things to sum to 0. So that's the goal now. So with those comments in mind, what it's enough to show that pi 1 with pi 1 on the not part is less than 1/2, because that will help bound this part here. But of course, that's the same as showing that on the regular semi-simple part, that's bigger than 1/2. And so all you have to do now is to calculate this thing with this condition here. And in fact, that's what Enyart did in the GLN case. So the Cauchy-Schwarz argument reduces to Enyart's thing. And basically, you can see that if it's, I actually didn't write it down, but it's something like, if the number of points that are not very regular is big enough, something like bigger than half of the size of the Weil group, the rational Weil group, then this statement will hold. So, and this statement holds if Q is sufficiently large. So that's the end of the proof. Okay, so now I've used up most of the time to talk about isomorphism on sale. Let me tell you about the application. So, and this is two representations of p-adic groups. Say again? Yeah. The root datum of, yeah. Okay, so here's what I'd like to do. Okay, so here's some cartoon that one can consider. So say I'm interested in a group like GLN of QP, which I'll write as G of F. Inside G of F, okay, so say I'm in some nice situation where I can also consider G of OF. Right? That's something that's sitting inside G of F, but obviously it's much smaller. But actually a lot of interesting things about G of F are remembered by this restriction to G of OF. Now G of OF is still an infinite group, and so maybe one thing that we can do is try to understand it by understanding some finite quotients of it. So I can consider G of OF divided by the unique maximal ideal inside OF. And this thing now, this object is now an object like in this statement, in this theorem statement right here. Right? So this is the depth 0 setting. But obviously by making pi f 0, you've lost a lot of information. Right? So how can you recover that? Well, maybe you don't make pi 0, you make pi squared 0 or pi cubed 0, etc. So you can play this game. And this thing is now depth r. Okay, and so the normalization r plus 1 here is just so that when r is equal to 0, it recovers this one here. Okay, So how do you build up representations over here? Well, you can choose something like this here, consider an interesting representation, pull back, compactly induce. You can do this all the way down. Okay? And this is the game that people play. Okay, so from now on, let me do the following thing. Okay. So in the depth 0 setting, it's exactly what I meant. Or okay, so for the rest of the talk, which is, I don't know, 10 minutes or so, I'm going to take T inside G to be an unramified maximal torus. And I forgot to put some notation over here. So in this kind of situation, at least in one's first pass, this thing I'm going to call G lower 0 of FQ. And this G of FQ will be like the G of FQs that we've seen. And then one construction that you can do, which probably many people in this room are familiar with, is one can take the Arth jet scheme associated to this scheme here. And that Arth jet scheme, if you take the FQ points, will just be this group. So I'll call this GRFQ. And you can do this for all the groups that we've seen. You can do it for T, you can do it for B, et cetera. Okay. Okay, so, huh? Yeah, so in equal characteristic, that's the meaning. In mixed characteristic, I mean, then what I really mean is that this thing, there's some scheme that has this property. I take, in general, what I want to do is I want to take a point in the building, I take a parahoric, I take a model for this, and then, but not only a model for this one, but a model for all its, the Moy-Prasad filtration, and then I take L plus of this, divide by L plus of this, and I claim representability. Perfect scheme, yes. Yeah. Okay. So I take this, and then I have associated to this all of these various GRs and TRs and so forth. Okay. So in the depth 0 setting, this means that if theta came from R is equal to 0, then work of Morris and Moy-Prasad, in the interest of time, I'm going to also assume that this torus is elliptic. But please know that there are statements that work outside of elliptic. Moy-Prasad said that, okay, well, this pi t naught theta that came from geometry, that came from Deligne-Lusztig, which I'll now write as geom here, this actually, when you take compact induction, you get a supercuspidal representation of the p-adic group. So I'll a bit change that to alg because it came from the algebraic thing of compact induction. Okay, what about positive depth? No, what? Huh? Irreducible, yes. Okay, so what if theta came from R positive? The first non-trivial setting where this case is interesting is under the conditions that theta has some genericity. Generic, I'll call it, TG generic. which is a root theoretic condition. It says that, I mean, theta is a character of this T, and this T has a filtration. It's a smooth character, so at some point it's going to be 0, and right before it's, at some point it's trivial, and right before it's completely constant, you just ask that it's as non-trivial as possible. So that's what this statement says. And this is work of Adler in, that says that 2 things. First, one can build a representation, TR theta alg, and that when you take its compact induction, you get something irreducible supercuspidal. Irreducible and therefore supercuspidal. Okay. So there's a general statement as well. So theta without this, so I'll just say in general position only. And this is done by combining work of JKU with work of Kaletha. The first statement is that one can build this pi tr theta in some algebraic way, and that when you compactly induce this representation, then you get this. You get an irreducible and therefore supercuspidal representation of G of F. Okay. Now, meanwhile, alongside this kind of thing, one can instead consider this geometric version, right? So over here, this was defined as the alternating sum of, I'll just write it as HC star, of the pre-image of U. And one can do that over here too. Geometrically, you can consider now like an RTR-GR theta, which is the version of this by taking now pre-image under the Langmack of the jetification of U. And this has the same properties as before. There will be an interesting, there will be a left action by GR of FQ, a right action by TR of FQ. One can consider the isotypic part with respect to theta, and then ask what representation of GR is that. And so we have a situation now where I can define for now TR theta, I'll say this plus Lusztig induction version, which is the generalization to where you allow T to be a levy, not just a torus. And then you can now have a geometric way to build have a TR theta geom. Okay. And so then a very natural question to ask is, well, what's the relationship between this representation and, say, in the simplest possible case, this representation, and more generally, this representation? When R equals 0, there's no difference already. Okay? And so for this reason, this is why Oye and I considered these kinds of things, is because we didn't know how to do this, right? When you're trying to understand whether two representations are isomorphic and say you have to calculate the trace on every element, this is something very difficult to do because usually character formulas are very intrinsic to how your representation was found, right? And so if it was found in algebra, the formulas that come in are very different than the formulas that come in if it was found in geometry. And so we tried to find some cheating way of doing this. Okay, so even more meanwhile, one can ask, given all of these supercuspidal representations that are on the BARD, how do they form, how do they interact with the Langlands program? And it's work of DeBacker and Spice in the TG generic case, and of Kaletha in general, So for theta in general position, that actually you don't quite want to take exactly these representations on the nose. So the parameterization, so t theta mapping to pi t theta, alg does not respect local Langlands. What's the thing that does is you need to twist to introduce a twist xi. And so the xi will appear here. So the correction is now you put a xi here, and then everything is fine. OK. So let me finish with maybe 2 statements. Since Oy and I have isomorphism on sale statements not only for g of fq, but also things like g of zp, then we can apply that situation to compare the geometric side and the algebraic side at the level of gr. So the first statement is that if you look at pi tr theta geom, OK, we need assumption on Q because we use isomorphism on sale. This thing is not, in fact, equal to this one, but is equal to the twisted one. And this is very good news. And the very good news is because it's now the one that does respect local Langlands. It's not the one that needed to be twisted. And the proof is really like you compute on the regular semi-simple part, on the version of regular semi-simple part. Over here on the geometry side, there's no choice. It always has to be an average over an orbit of thetas. But over here, when you compute, you see this xi popping up. And so you have to overcorrect for this. OK. Oh, yeah. This is difficult. So sometimes xi is the trivial character, actually. It's in the simplest case, in the TG generic case, it will be trivial half the time, and roughly half the time, and not trivial the other half the time. I mean, half is kind of misleading also. OK, so I won't be able to define it for you, but let me tell you when it's interesting. So in the construction of JKU, half the time you can just follow through and construct the representation easily. And in that kind of setting, there's no such issue. But sometimes you have a situation where you'd prefer to have a representation of a slightly bigger group because the one that you have right now doesn't induce irreducibly. But the only way to kind of get a little bit bigger is to use Weil-Heisenberg representation. And all places where you use Weil-Heisenberg representation will introduce some non-triviality inside this xi. Yes, it's order 2. I thought, yeah, it's quadratic character. It just has values in plus or minus 1. OK. So in the last negative 1 minute, let me say one thing about character sheaves. OK. So far, I've said things like, oh, you have this representation, but actually you only cared about the regular semi-simple part, and that determined everything, right? But a very natural question to ask is like how you can recover the rest of the representation, yes? And this is like not a natural thing to do in representation theory. Like you take a class function, you restrict it, and you're in some discrete setting. There's like you can't. It's very difficult to do. I don't know any representation theoretic way of doing this. But in analysis, you can do this if you are in a kind of more continuous setting, right? Like this is like you take a continuous function on GL2C, and you say, I know what it is on the regular semi-simple part, then obviously you know what it is everywhere because you just walk. You take limit, right? And so everyone in this room will know what you do in algebraic geometry, which you take intermediate extension. Yeah. So here's the theorem. Due to Lusztig, which is that if you take the intermediate extension of the version of this orbit over W, which is looks like this, I won't explain further than this, and you take its trace of Frobenius, then what you get is pi t0 theta geom. So this is Lustig's famous theorem in 1990. Okay. Oh my God, no, I just forgot. Yes, yes, no, yeah. Okay, so this was the case so this is a very beautiful story, and part of this thing uses the geometric version of parabolic induction, which I wrote down the character formula for parabolic induction at the beginning, but that formula can also be viewed as the formula that comes out when you do a push-pull along the Grothendieck-Springer resolution. So you have this kind of thing. This thing, okay. And you have I'll go a bit fast here. And so a key point here is that in this setting, this pi here is small and proper. Small or just semi-small? Okay. Okay. However, say I wanted to understand what's happening for the jetifications, the Arth jet schemes. This thing is no longer proper, and is also no longer small or even semi-small or anything like that. And so conjecture of Lusztig was to make sense, to ask if you have some local system on your TR that has some sufficiently generic condition like TG genericity, that the pullback and push, that thing should still have nice properties. In particular, it should be a simple perverse sheaf. And so we now know this, and this is work joint with Bezrukavnikov and myself. And what we can show is that and on top of that statement, resolving Lustig's conjecture, we can say that when you calculate the intermediate extension of this thing, you get pi tr theta geom. So the picture then is that geometric parabolic induction, even in positive depth, this thing gives you this twisted, or I'll just say positive depth Deligne-Lusztig induction. And this thing, so this is from BC 24. Okay, well, it's there. And this thing here, by this first statement over here, gives you the twist of JKU's construction. FKS, Finson, Kaletha, Spice, twist of JKU's construction. And so something quite interesting here is, this is really something that's giving you supercuspidals. This thing is also feeding in something that's elliptic, but this is really making use of the fact that all of these things geometrically become split. And so just in terms of geometry, it's really just classical parabolic induction. It's just when you take the trace of very interesting Frobeniuses that you actually get all this cuspidal stuff coming out here. Okay, I'll stop here. Sorry for going over time.
Questions?
Right. Yes, what do you use instead of a smallness in that theorem?
Yeah, so basically what we do is, everyone's favorite thing about connective reductive groups is that it has Bruhat decomposition. But when you put an R here, it no longer has Bruhat decomposition. It has this extra piece that comes from the kernel to G0. And so basically the whole thing is about saying, okay, well, if you have some local system that has TG genericity, then that TG genericity basically allows you to get rid of this contribution over here. And so it allows you to pretend like you're only on the Bruhat part. And the Bruhat part is really the thing that's controlling the behavior of this situation. And so what we show is that we construct, inside the equivariant derived categories on these GRs, we construct some generic subcategories, which are like subcategories of things that have nice equivariance with respect to the deepest part, which is like a Lie algebra condition. So it's like Fourier transform support kind of condition. And in this situation, we show that actually parabolic induction induces an equivalence of categories. And so it's actually even more special than in the depth 0 setting where you don't have an equivalence of categories. And you have an equivalence, and then we show it's T-exact, and so then perverse things go to perverse things, simple things. Yes. Correct. Yes. Yes, okay. So this sufficiently generic condition is about like geometrically it's saying you have all these co-roots and you can pull back to these GAs and you ask that it's a non-trivial local system on the GA for all the co-roots. Okay, so say you only want to do this for some of the co-roots. Then what you can do, and we do this in the paper, is that instead of inducing from T, you're then allowed to induce from a bigger group. So by enlarging where you came from, you can weaken the genericity condition required on this deepest part. And so in particular, this deepest condition will then be like, for all the co-roots outside of your levy, then you have this non-trivialness condition. And what you can then do is you can kind of inductively work with these scenarios, right? You induce to as wide as you can without breaking your genericity. And then there's some way to build up a bigger thing that has, this is somehow built up in this construction over here where the data here comes from a sequence of twisted levies together with some, and then so you keep doing this to make something wider, build something wider and wider and deeper. And so at each particular step, you really only need one genericity, but that one genericity is just like, it's weaker as long as you know a bigger thing that it came from.
Any other questions?
Thank you.